Very good morning, students. Today, I will explain the a very little bit portion that is the left in the module 1 and which is known as Brillouine zone from the band theory of the solid. Okay, here I have not given any heading because all details are given in your PDF lecture. I will just explain the diagram and related theory information that will help you to get understand that what do you mean by Brillouine zone with the concept of the band theory of the solid, right? Okay, so already we have covered the most of the portion of the module 1. I am just doing a quick recap from quantum mechanics, quantum physics, from the concept of quantum physics, Schrodinger time dependent equations and their related derivations, proof, everything, related formulas, number of formulas are there, and all are very much important for you to get understand the line by line, each and every line, right? So there are different kinds of formulas are there and different kind of parameters, and each and every parameters are unique. They are differentiable from each other, and all must have a unique property also. From that, how to solve these kind of equations from the concept of boundary conditions, by applying the concept of boundary conditions, and the concept of particle in a box, the concept of infinite potential well, and why I am giving focus on this potential well, because this potential well is related to explain this Brillouine zone, okay, inside the lattice, right? We are considering a crystal, and inside the crystal of a lattice we will describe the particle movement, the electrons movement, by doing some graphical representation, and will divide into some zone, and where the energy is continuous and energy is discontinuous. Therefore, we have drawn a graph versus E and K. We all know what is E and K. E is nothing but energy and K is nothing but a wave vector, right? So we have already done the particle in a box concept and the related derivations, the energy diagram, and the inside the solids, if we can say that, all kinds of your conductor, insulator, metal, the energy band diagram, everything we have already covered. And in a previous lecture, I have introduced a new concept, that is the chronic penny model, and with Bloch's theorem, and the density of states, the concept of degeneracy, a huge number of topics were there in a module 1 and totally new in a nanoelectronics part. So please go through all the related video lectures, all the related PDF, the related books that I have already shared in a Google Classroom, and to get understand very well, and please do practicing, otherwise you will not be able to get understand each line, because each and every topic, each and every portion are related to each other. So if you neglect the previous one, the current portion will not help you to get understand properly, right? Okay, so I will focus on today's topic. So here I have drawn a graph in between E and K, okay, and we have seen that there is a parabola, right? So what is this parabola? This is nothing but the energy graph, right? Somewhere the energy is increasing, somewhere the energy is decreasing. So if we do the graph, if we draw the graph, it will look like this, okay. And I will tell all the details in the next lecture, because this lecture is only about by explanation of this diagram, and the related derivation I will do in the next lecture. So see, these curve I have mentioned with E means En, that I described, that I derivated in the solution of time independent equation. So E in what value we got? The value we obtained, that is h cut square k square by 2 pi square m. This is the final expression of the discrete energy states, right? And if we put h cut equal to h by 2 pi, we will get this kind of expression, h square k square divided by 8 pi square m. So it is nothing but the discrete energy level, and this is the see, this is the there is some zone. I have divided some zone, and this kind of zone that I have shaded over here, that is nothing but the allowed zone. Okay, that is nothing but the allowed zone. And what is Brillouine zone? The Brillouine zone is in between minus pi by a to plus pi by a. And similarly minus 2 pi by a to plus 2 pi by a. And how it is happening, I will all explain. Don't worry about that. So here I am just doing the a little bit explanation. That is, it is nothing but the graphical representation of E and the wave vector k. Right? And we generally assume that the energy is continuous. Right? We have already seen that energy is continuous. But here we are seeing that energy is discontinuous. Somewhere energy is discontinuous. See, in this portion, in this portion, in this portion, in this portion, that there is a discontinuity, and only the continuous portion I have dotted this is as a zone, and this is nothing but the allowed zone. Okay, so why, my question is, why this process is happening, why there is some discontinuity, right? So here the zones are formed where the energy is continuous, like this portion, and this portion, and here it is repeating. So energy is continuous. Where the energy is continuous and a zone is formed related to that is known as allowed zone. And in this allowed zone, why it is called allowed zone? Because in this allowed zone the electrons takes place at some particular state, right? At some particular state, because you already know the forbidden zone, allowed zone, energy band gap, and everything, then all the concepts are coming out from this this point of view. So in this allowed zone the electrons takes place at some particular state, so that's why it is called the allowed zone. And the distance between these allowed zone, see there is a gap, so the distance between each and every allowed zone is known as forbidden zone. All I have marked in my PDF lecture, so please go through that. I am just explaining the briefly, very briefly. And the distance between these allowed zone, like this portion, this is the blank portion, is known as the forbidden zone, right? So energy spectrum of an electron moving in the presence of the periodic potential field is divided into two zones. One is your allowed zone and one is your forbidden zone, right? So please notice that electron is not continuously moving. Somehow it is moving, somehow it is scattering, somehow it is colliding with another particle. So that's why energy is not continuously nature in the inside of the lattice, inside of the crystal. So that's why where the energy is continuous, we will call it as a allowed zone, and where the energy is discontinuous, we will call it as a forbidden zone, right? So we can say that the energy spectrum, if we draw the energy spectrum of the particle moving in the presence of the periodic potential field inside the crystal, is divided into two zones. One is this dotted line, dotted zone means this is allowed zone, and this blank zone, that is the forbidden zone, right? And with this diagram we will explain that what is Brillouine zone, right? So please continue with the PDF lecture. I will discuss in detail in the next lecture.